Go for the first chapter for design and analysis of algorithms. Okay, so DAA for sure. So the first chapter was quite straightforward, I'd say. It's just an introduction to some sort of concepts and just time complexity, say. So we start off with algorithm. Definition for that is a finite set of well-defined instructions for accomplishing some tasks. And the two things that we really care about is correctness and efficiency. And by efficiency, what we mean is runtime. So just how long would it take using the big O notation. So then there's sort of things that are kind of talked about was, I guess I just wrote this for myself, insertion sort, because I'm always confused what it means, is always add one element to the correct spot in a sorted array, because there are several different sorts, and I just always mix them up. In this, we can just do this is just common, and then you definitely do want to make sure that you talk about loop invariant, which is just for showing that it's actually, I mean, not showing, like fully proving that it's correct. So we kind of have three kind of main things to justify in a loop invariant. So we have the initialization, which is like the base case. So we want to show that the invariant is true before the loop. Second one is that maintenance. So like basically it's like the inductive step. If the invariant is true before the iteration, then it remains true after the iteration executes. So basically, in other words, executing in this loop doesn't change the invariant from becoming, if it was true, then it's still true. And then the last part is that it'll terminate and it's going to be true. So reason why loop will stop, so that's usually talking about the variant, finding a variant that decreases and will tend to zero. And then obviously getting the final result that means that the loop invariant is still true. And after doing all of these loops, our runtime would just be all of the statements that we used, their cost times the number of times they were executed. So it makes a lot of sense. These are just some notation that was kind of like the formal notation for showing like big O of n. Basically, f and g are functions, and what we do is we define the set of O of g of n. So it's actually, we write O of g of n equals, but in reality it's a set, right? Where f is into r, and then there exists some and not that's part of the natural numbers. There exists C inside this real number that's positive for all n is greater than or equal to the starting value of the n of f of n is smaller than or equal to C times G of n. So the idea is that's the set, and then basically the idea is that there is a positive constant such that basically, this is always smaller than or equal to sometimes c times a constant times something. So it's basically g is a asymptotic upper bound for f. So we have something that caps it off. That's the idea. I don't really like this like formal thing, but I think the idea is that we kind of treat O as a set rather than actually equals, because equals is just our sort of simplified way of writing something. So yeah, so some simple things that we should know. For instance, if we have log C of n with C as a constant, then it definitely belongs in a set of O of n of d, because we can definitely represent with some constant d to this thing, right? And then for instance, n of c is part of the set of O of d of n, because obviously if you have a polynomial versus an exponential, obviously the exponential is greater, so the O captures that. So yeah, basically that's the idea. F of n is equal to this. We can just say part of this, we could just simplify and write it as equals. And then there's just some notations to be familiar with that are reviewed from discrete math. This omega basically represents asymptotic lower bound. And then theta is type bound, and O is like the worst case bound. And then some simple math review, log review, is that A equals B of log B of A. Obviously, log B of A is equal to, you can write a different base constant and then just do A and B like this. You can also swap B and A, but 1 over that. Or you can do swap A and C, basically like this. Pretty straightforward math properties. And then a formula to know because there's a lot of n factorial, because in fact factorial it's kind of hard to represent itself. So we just approximate it to be, this should be approximate, but yeah, approximate it to be square root of 2 pi n times n to the n divided by e to the nth times 1 plus theta of 1 over n. But essentially we can just, I think I just remember it as theta of 2 pi n times n divided by e to the n. That's kind of what I remember. I just go by that. Because this thing over here, 1 is just keeping this constant. As n grows large, this thing is pretty small, so it tends to 0, it doesn't matter for us. So this is just a generic kind of overview of the order of magnitude. Obviously, 1 is like the constant, yeah, the best. Log of something, yeah, small. Log of n, okay, pretty good. Log squared or log cubed, okay, all right. N, okay, that's linear. Then we have n log n, which is basically, this is kind of like, ideally, most of the time we do want to aim for this. And then there's n squared, and then we get the exponential terms, then we get the factorial, then we get things that stack on top of each other. Like that's just insane. And a useful bound that comes up a lot that is good to be familiar with is this. N divided by 2 to the n divided by 2 is smaller than or equal to n factorial or smaller than or equal to n to the n. Why is this the case? Because if we write out n factorial, it would be n times n minus 1 times all the way to 1. And there's n terms, right? N to the n is all the terms with n. So obviously we can see that n minus 1, n is greater than that, and every term inside the n is greater than these terms. So then this is obviously the larger term. And for n over 2 times to the n over 2, the first n over 2 terms are all less than n, right? Because each one are n over 2. And each one, these over here, because this point is n over 2. Obviously, these are less. And then on the right-hand side, everything is 1, because basically the rest of the terms would just be thought of as 1 times n minus 2, right? Something like of this form. And then this is just all 1, which is definitely usually less than the side. So definitely, yeah, both are smaller, then this equality holds. Yeah, that takes me to the end of this chapter. I think it was sort of easy in the first week to kind of just get familiar with the notation. Definitely the loop invariant was a new concept and just getting familiar with the set notation. I didn't know before that it was a set. I just thought it was just equals. And yeah, the rest are, I'd say, pretty straightforward.